Welcome to the deep dive. Today, we're plugging into something, well, pretty fundamental, isn't it? That invisible force powering our daily lives, household electricity. You asked us to sort of unravel how this power actually travels to your appliances and also the ingenious safety measures built into the whole system.
Exactly. And we've got a fantastic, really comprehensive chapter here on household circuits to explore. Think of this as your backstage pass, if you like, to understanding the magic happening behind those wall sockets.
Yeah, our mission today is pretty straightforward. We want to illuminate the key insights, maybe reveal some surprising facts, and equip you with practical knowledge about your home's electrical system. And all without getting bogged down in, technical gobbledygook.
Okay, let's dive in then, starting right where the power's journey begins. From the power plant to your trusty plug.
Right, and what's fascinating to begin with is the initial voltage right there at the power generating station. It's around 11 kilovolts typically.
11 kiloV. Why that specific level? Well, it seems to be a kind of balancing act. Generating at much higher voltages brings up significant insulation challenges. But if you generate at lower voltages, the currents involved would be incredibly high, which also causes problems.
Okay, so 11 kV is the starting point. But it doesn't stay that way for long, does it? Especially when you're talking about sending it across the country. Why do we need those, super high voltage transmission lines?
Well, if we connect this to the problem of energy loss, it really boils down to heat. Simple as that, really. Think of it like this. Any current flowing through a wire generates some heat, right?
Yeah.
And that heat is just wasted energy. Now, the power lost as heat, it's proportional to the square of the current. I2 Rollers.
Right, the square of the current. So a little more current means a lot more heat loss.
Exactly. But for a given amount of power, power equals voltage times current. So current is inversely proportional to voltage. P equals V times I. So I equals P over V. So if you crank up the voltage way, way high for transmission.
The current goes way down.
Precisely.
Yeah.
And if the current is drastically reduced, then the energy lost as heat, $2,000 in those long transmission lines, is also massively reduced. High voltage is like an electricity superhighway, minimizing those energy loss traffic jams over long distances.
Ah, I see now. Okay, high voltage, low current, less waste. Makes sense. So how does that initial 11 kV get boosted up to those transmission levels and then crucially back down safely to something our homes can actually use?
Yeah, that's where transformers are the key players. At the generating station, or what they call the grid substation, step-up transformers increase the voltage dramatically. So from that 11 kV, it goes up to maybe 132 kV, sometimes even higher.
Wow. Yeah.
And this really high voltage travels along the big transmission lines to what are called main substations. Their step-down transformers reduce it, maybe to around 33 kV. This often supplies heavy industries directly.
Right, they need a lot of power.
Then, from there, it goes to intermediate substations, step down further, perhaps back to 11 kV for lighter industries or maybe smaller towns, city substations.
Yeah.
And then finally, at the city substation near our homes, another set of step-down transformers brings the voltage right down to the familiar 220 volts or 240 volts that powers most homes.
It's quite a journey, like a carefully planned voltage roller coaster, stepping down at each stage.
Exactly. A step-by-step descent to a usable, safer level for us.
So once it finally reaches our house, what does that electrical cable actually look like? I know there are usually 3 wires inside, not just 2.
You're right. The cable bringing power into your home typically has 3 insulated wires inside. There's the live wire, usually labeled L,
Okay.
the neutral wire, N,
N,
and the earth wire, E.
L, N, and E.
Got it. Now, what's really crucial to understand here, and this is key for safety, is that the neutral wire and the earth wire are actually connected together, usually back at the local substation.
Connected together. So what does that mean electrically?
It means they are essentially at the same electrical potential, which is intended to be 0 volts or earth potential.
Okay, so neutral and earth are both sitting at 0 volts. So what are the specific jobs of the live wire and the neutral wire then in the circuit?
Well, the live wire, as the name kind of implies, carries the alternating current at the high potential, the 220 volts from the power source towards your home's main distribution board. The neutral wire, being at 0 potential, provides the return path for this current, completing the electrical circuit after it's done its work in your appliances.
Ah, okay, so it's like a two-way street. Live is the out lane with the power, and neutral is the back home lane for the current.
That's a good way to think about it, yeah.
Okay. Now, before the electricity even gets to our meter, I remember reading something about a company fuse. What's that all about?
Ah, yes. The company fuse. Sometimes it's called the pole fuse if it's up on the utility pole outside. It's a pretty high-rated fuse, typically around 50 amps, maybe more depending on the supply needed. And it's connected in the live wire before it even reaches your electricity meter.
For the meter. Okay, so what's its purpose?
It's basically the power company's first line of defense. It's primary protection for the entire connection, from their infrastructure right up to your property boundary. And importantly, only authorized people from the electric supply company are allowed to access or replace it. Its rating depends on the total load your connection is designed for.
Gotcha. So that's the power company's responsibility. What happens right after that company fuse then?
Right after the company fuse, the cable runs to your kilowatt-hour meter, the kilowatt-hour meter. This is usually fixed to an outside wall or in a box somewhere accessible, and it does exactly what the name says. It measures the electrical energy you consume over time, which is what you get billed for.
Okay, the meter. Then what?
Following the meter, the cable enters your house, typically going to the main switch and the main fuse, or more commonly these days, a main miniature circuit breaker, an MCB.
Ah, MCBs. So these miniature circuit breakers, they're like smarter, reusable fuses, essentially.
That's a great way to put it, yes. We'll probably talk more about them later, but they react to overcurrents like fuses, but can just be reset.
Okay. And I noticed the text mentioned the main switch is often a double pole switch. What's the significance of that? Double pole.
Good question. A double pole switch is designed so that when you switch it off, it breaks the connection in both the live and the neutral wires simultaneously.
Both wires. Why?
It's an extra safety measure. It completely isolates your home's entire electrical system from the incoming supply, cuts off both the power in and the power return path at the same time. That main switch usually has a metal covering too, which itself is earthed for safety.
Okay, total isolation. But you said the main fuse or MCB is usually only in the live wire.
That's right. The main overcurrent protection device, whether it's a fuse or an MCB, is typically placed only in the live wire after the main switch.
Interesting difference. So main switch cuts both.
Yep.
Main fuse MCB, just the live. What about this consumer unit that was mentioned, with its own switches and MCBs inside the house?
Right. The consumer unit, or sometimes called a fuse box or distribution board, is essentially the central hub for all the circuits within your home. It comes after the kilowatt meter and the main switch. Inside, you'll usually find another main switch, often a double pole one, or perhaps an ELCB, an earth leakage circuit breaker.
ELCB, what's that?
An earth leakage circuit breaker. It's another type of safety switch, very sensitive. It looks for any tiny currents leaking from the live wire to the earth wire, which could happen in a fault. If it detects a leak, meaning current might be flowing through something it shouldn't be, maybe even a person, it trips the circuit extremely quickly.
Wow, okay.
Very sensitive.
Yes, so the consumer unit has that main switch, or ELCB, for overall protection, and then a row of individual MCBs, one for each separate circuit in your house. You know, one for the downstairs lights, one for the upstairs sockets, one for the cooker, and so on. This gives you more localized protection. If one circuit trips, the others stay on. Okay, that makes sense. A central distribution point with individual protection. So that's the power making its way into the house and getting divvied up. Now, the chapter talks about something called the ring system, or ring main for house wiring. That sounds intriguing.
Yes, the ring system is quite common, especially in some regions like the UK. It's a specific way of wiring the sockets in a house, instead of running a separate cable from the consumer unit to each individual socket.
Which sounds like a lot of cable.
Exactly. In a ring system, a single cable starts from an MCB, say a 30 amp one, in the consumer unit. It then loops around all the sockets in a particular area or floor of the house connecting to each one, and then the cable returns right back to the same MCB terminal it started from, forming a complete ring or loop.
A loop. So it goes out, visits all the sockets, and comes back to where it started. Huh. What's the advantage of wiring things up like that? Seems a bit counterintuitive.
Well, there are actually several key benefits. Firstly, because it's a ring, the current can actually flow to any given socket or appliance from two different directions along the cable. Ah, okay, like it has two paths to get there.
Precisely. Effectively, this means the two halves of the ring are electrically in parallel. This allows the system to use a thinner, less expensive cable for the ring itself than you'd need for a single radial circuit carrying the same total load. It's a clever way to get the current carrying capacity without needing super thick, costly copper wire running everywhere.
Okay, cost saving using thinner wire because of the two paths. What else?
Secondly, Each appliance plugged into a socket on the ring usually has its own fuse fitted right inside the plug itself.
Right, those little cartridge fuses and UK-style plugs.
Exactly. So if a fault occurs in, say, your toaster, the fuse in the toaster's plug should blow first. This isolates just the faulty coaster, but it doesn't affect any other appliances plugged into different sockets on the same ring circuit. They keep working.
That's definitely a good fail-safe. Keeps the problem localized. And what about adding new sockets or appliances later on? Is that easier with a ring? Generally, yes. Because the ring cable runs around the area, you can often add a new socket by spurring off an existing one, or sometimes by cutting into the ring cable itself, following specific wiring regulations, of course. You don't necessarily have to run a completely new cable all the way back to the consumer unit as long as the total potential load on that ring doesn't exceed the rating of its MCB, which is typically around 30 or 32 amps.
So more flexibility.
Yes, and it also allows for a standard size of socket to be used everywhere, with the specific protection tailored to the appliance by the fuse in its plug.
That sounds like a pretty clever and efficient system, actually.
Yeah.
Now, when we plug in all our different devices, lamps, TVs, chargers, they all connect it in the same way electrically within the house wiring. The chapter mentions parallel versus series connections.
Yes, this is absolutely fundamental to how household circuits work. In our homes, virtually all electrical appliances, your lights, your sockets, your built-in oven, everything are connected in parallel with the mains supply.
In parallel. Okay, what does that actually mean for how they operate day to day?
Well, connecting them in parallel means that each individual appliance is connected directly across the full mains voltage, so across the live and neutral wires. This ensures that each device receives its proper rated voltage, say 220 volts, so it can operate correctly and deliver its intended power output.
Okay, so everyone gets the full voltage.
Right. And crucially, in a parallel circuit, each appliance can be switched on or off independently using its own switch, which is always placed in the live wire feeding it. You can turn on the kitchen lights without the microwave starting. You can use the vacuum cleaner while the TV is off. They don't affect each other's operation, electrically speaking.
That makes total sense. We definitely wouldn't want, all the lights dimming when the kettle boils or everything going off if one bulb blows.
Exactly. Independence and rated voltage are the key advantages.
So why don't we ever see appliances connected in series in our homes? It must be possible, but why is it a bad idea?
Oh, it's a very bad idea for household wiring for several reasons. Firstly, if you connected appliances in series, the total voltage from the main supply would be divided among them. So if you had, say, two identical lamps in series on a 220V supply, each lamp would only get about 110V across it. Neither would light up properly, if at all, because they're designed for 220V.
Okay. Voltage division. They wouldn't get enough power.
Right. Secondly, adding more appliances in series increases the total resistance of the circuit. Higher resistance means lower current overall from Ohm's law, IVR. So adding more devices would actually make all of them dimmer or run slower.
That seems backwards.
It is for how we want things to work. And thirdly, and perhaps most inconveniently in a series circuit, if any one appliance is switched off or if its filament breaks like in an old light bulb.
The whole circuit is broken.
Exactly. The entire chain stops working. Everything has to be on, or trying to be on, for anything to work. Imagine your Christmas tree lights, where if one bulb goes, the whole string goes out. That's often a series connection.
Ugh, the dreaded Christmas light hunt. Okay, that paints a very clear picture of why series is no good for general home use. The chapter used light bulbs to illustrate this, didn't it? And even mentioned something about car lighting.
Yes, it did. It used the example of connecting bulbs in series versus parallel to show the brightness difference. In series, they're dim. In parallel, they get the full voltage and are bright. It also mentioned that some older car lighting systems might have used series connections, say for taillights, which could explain why they might glow dimly. Modern cars, just like our homes, use parallel connections for reliability and proper brightness.
Right, and didn't it also mention car lights dimming when you start the engine?
Yes, that's a parallel circuit effect too. The starter motor draws a huge amount of current from the battery when it starts. This large current causes a temporary drop in the voltage available at the battery terminals, and since everything else, like the headlights, is connected in parallel to the battery, they dim momentarily because the voltage they're receiving dips slightly.
Okay, interesting. So parallel is definitely the way to go for our homes. Now, let's circle back to those little guardians we mentioned. Fuses. We keep saying they're important for safety. What exactly is a fuse, and how does it keep us safe?
Okay, so a fuse, at its most basic level, is a deliberate weak link in an electrical circuit. It's a safety device specifically designed to limit the amount of current flowing through that circuit.
A weak link.
Yeah, think of it like a sacrificial component. Its job is to fail safely to blow or melt if the current gets too high for any reason. This protects the rest of the circuit, especially the appliance connected to it and the house wiring itself, from damage due to overload or a short circuit.
Okay, so it breaks the circuit if there's too much current. How does it actually do that? What's the science bit?
It works based on the heating effect of electric current, which we touched on earlier with transmission lines, I2 rise. When current I flows through any material with resistance R, it generates heat. A fuse contains a very specific type of wire, the fuse wire. This fuse wire is designed to be short, thin, have a uniform cross-section, and possess two key properties: relatively high resistance compared to the circuit wires, and crucially, a low melting point.
Low melting point. What kind of material is it usually made of?
It's typically an alloy of lead and tin. This alloy melts at a fairly precise and relatively low temperature, around 250 degrees Celsius.
Okay, 250 degrees C. So why not just use a thin piece of regular copper or aluminum wire? They conduct electricity well, right?
They do, but that's actually the problem. Copper and aluminum are excellent conductors with low resistance and much, much higher melting points. Copper melts around ever 80 degrees C. If you used a thin copper wire as a fuse, by the time enough current flowed to heat it up to its melting point, that same current would likely have already caused significant damage or overheating in the appliance or the wiring you're trying to protect. The fuse needs to be the first thing to go reliably at a specific current level.
That makes perfect sense. It has to be specifically engineered to fail first.
Yeah.
What does a typical household fuse look like? The replaceable kind.
A very common type, especially the ones used in plugs or older consumer units, consists of the special fuse wire stretched between two metal end caps or terminals. This whole assembly is then housed inside a small casing, often made of porcelain or ceramic, because those materials are good electrical insulators and can withstand the heat when the fuse blows. This fuse holder then fits into a fuse carrier or socket, which is physically connected in series with the live wire of the circuit it's protecting.
Always in series with the live wire. Okay. And so when the current surges, what actually happens inside that little porcelain tube?
Right, so if the current flowing through the circuit exceeds the fuse's rated value, say a 5-amp fuse experiences 10 amps due to a fault, the fuse wire heats up very rapidly because of its resistance, I2I dollars again. Its temperature quickly rises past its melting point, the 250 degrees C or so. The wire melts, creating a physical gap in the circuit. This break instantly stops the flow of the excessive current, protecting everything downstream.
And it stays broken until you replace the fuse.
Exactly. For more sensitive or expensive appliances, you often find cartridge-type fuses, which are similar but often glass tubes, designed for very specific ratings.
Okay. Now, we've established they're crucial safety devices, and you've mentioned a couple of times they're always connected in the live wire. Why is that specific placement so critically important? Why not the neutral?
This is an absolutely vital safety principle. Putting the fuse in the live wire is non-negotiable for safety. Think about what happens if the fuse were in the neutral wire instead. Imagine an overload occurs. The fuse in the neutral wire blows.
Okay, so the circuit's broken, right? The appliance stops working.
The appliance stops working, yes, because the return path is broken. But the appliance itself is still connected directly to the high potential 220V of the live wire. If someone then touched that appliance, especially if it had a metal casing, they could still get a severe electric shock because the current would try to find a path to Earth through their body.
Wow. Okay. That's bad.
Very bad. By placing the fuse in the live wire, when it blows, it completely disconnects the appliance from the high voltage source. The appliance becomes dead, making it safe.
That's a really, really important distinction. Live wire only for fuses.
Got it. So how do we know what current rating a fuse should have? You mentioned 5 amps, 50 amps.
Yeah.
How is that decided for a specific circuit or appliance? The general rule is that the fuse rating should be just slightly higher than the maximum normal operating current that the circuit or appliance is expected to draw. You can usually calculate the normal operating current using the power formula. Current in amps equals power in watts divided by voltage in volts, so I equal PV.
Okay, IPV.
So for general lighting and fan circuits, the total power is usually quite low, maybe only a few hundred watts. The current draw is small, so the wiring is often thinner and protected by a lower rated fuse, like maybe 5 amps. But for circuits supplying high-power appliances like electric heaters, ovens, kettles, or air conditioners, these draw much more current. They need thicker wiring and fuses with higher ratings, maybe 13 amps, 15 amps, or even 30 amps for something like a big cooker.
So if I have, say, a 1,000-watt heater running on 220 volts, the current is 1,000 divided by 220. That's about 4.5 amps. So a 5-amp fuse would probably be the right choice there.
Exactly. 5 amps would be appropriate. You need a rating slightly above the normal running current, but not too much higher. Otherwise, it won't provide proper protection against smaller, sustained overloads.
What about things with motors, though? The chapter mentioned something about starting current. Does that complicate things?
Yes, that's a very important consideration. Appliances with electric motors, think refrigerators, washing machines, vacuum cleaners, power tools, water pumps, often draw a significantly higher current for a brief moment when they are first switched on. This is called the inrush or starting current.
Higher than their normal running current.
Yes, sometimes several times higher, just for a fraction of a second while the motor gets up to speed. The fuse protecting such an appliance needs to be rated slightly higher than this peak starting current. Otherwise, it would just blow unnecessarily every single time you tried to turn the appliance on, which would be very annoying.
Ah, okay. So you need to allow for that initial surge.
Mm-hmm.
The example was a water pump running at maybe 6.8 amps, but starting at 10.4 amps.
Right. So for that pump, you wouldn't use a 7-amp fuse. You'd probably need something like an 11-amp or maybe even a 13-amp rated fuse to handle that starting kick, even though it normally runs at under 7 amps.
Got it. Alive for the kick. And we mentioned MCBs earlier as the modern alternative. What are the main advantages, again, of using MCBs instead of old-style fuses?
Right. Miniature circuit breakers. They offer several key advantages. Firstly, they generally react faster. They trip more quickly than a fuse melts, especially for large overcurrents like short circuits. Secondly, they're reusable. After an MCB trips due to a fault, and you've hopefully fixed the fault, you simply reset it by flipping the little switch back up. No need to fiddle around finding and replacing a fuse wire.
Much more convenient.
Definitely. And arguably safer, too, because there's no risk of someone getting frustrated and putting in the wrong rating of fuse wire. Or worse, bypassing the fuse altogether with a bit of ordinary wire, which completely defeats the protection. MCBs have fixed, reliable trip settings.
That makes a lot of sense. Faster, reusable, fixed rating, safer overall. Okay,
Right.
Now let's move on to another crucial component we use every day, switches. They seem simple on, off, but I guess there are important safety aspects here too.
Absolutely. A switch, in its basic function, is just an on-off device used to make or break an electrical circuit, controlling the flow of current to an appliance or light. And just like fuses, for safety reasons, switches are almost always connected in the live wire.
Okay, again, the live wire. We touched on this with fuses, but why specifically the live wire for a switch? Same reason.
Pretty much the same fundamental safety principle, yes. By placing the switch in the live wire path, when you turn the switch to the off position, you are physically disconnecting the appliance from the high potential, the 220V of the power supply. This ensures that even if the appliance is still connected to the neutral wire, which is at zero potential anyway, the appliance itself becomes dead and safe to handle, clean, or maybe even perform minor maintenance on, like changing a light bulb.
Right. So what's the danger if someone wired a switch incorrectly into the neutral wire instead?
If a switch were mistakenly placed in the neutral wire, turning it off would indeed interrupt the return path, and the appliance would stop working, so it looks like it's off. However, the appliance would still be connected internally to the live wire, and therefore its internal components would remain at the high 220V potential relative to Earth. If someone then touched a conductive part of that appliance, or if there was an internal fault where the live wire touched the casing, they could receive a nasty shock because the path to live potential is still there, even with the switch off.
That's a really scary thought. It looks off, but it's still dangerous.
Wow. Highlights why proper wiring is just so critical. The chapter also mentions single pole versus double pole switches. We talked about the main switch often being double pole. What's the difference generally? A single pole switch, which is the most common type you find controlling individual lights or sockets, just has one set of contacts. It only interrupts or connects the live wire. A double pole switch, as we discussed for the main switch, has two sets of contacts that operate together. It simultaneously interrupts or connects both the live and the neutral wires, providing that more complete isolation from the supply. You sometimes see double pole switches for high-power fixed appliances too, like cookers or showers.
Okay, single breaks the live, double breaks both live and neutral. And what about those clever switches you get for staircase lighting? where you can turn the light on at the bottom and off at the top, or vice versa. Are they a different type again?
Ah, yes. Staircase wiring uses what are called two-way switches, or sometimes three-way switches, depending on the terminology used. They are indeed different internally. A standard single-pole switch is just on or off. A two-way switch doesn't really have an off position. Instead, it connects a common terminal, usually connected to the live wire or the switched live going to the lamp, to one or the other of two traveler terminals. By using two of these switches, wired correctly with traveler wires running between them, you create a circuit where flipping either switch changes the state of the light, on to off or off to on, regardless of the position of the other switch.
That is pretty ingenious how flipping either one reverses the connection. Clever. Now, a really basic but absolutely crucial safety tip that was mentioned is never ever touch switches with wet hands. Seems obvious, but why is that so important electrically?
It seems obvious, but it bears repeating because water significantly lowers the electrical resistance of your skin. Pure water isn't a great conductor, but the water we usually encounter has impurities, salts, making it conductive. If you touch a switch, especially one that might have slight damage or condensation around it with wet hands, that water can create an easier path for electricity to flow from the live parts of the switch through your body to Earth. This dramatically increases the risk of receiving a severe, potentially fatal electric shock. It's a fundamental rule. Always make sure your hands are completely dry before touching any electrical switch, plug, or appliance.
Yeah, absolutely. I remember getting a tiny buzz once from a light switch after washing dishes.
Huh.
Definitely makes you careful.
Exactly. It's a lesson you don't want to learn the hard way.
Okay, very important reminder. Let's move on to another absolutely vital safety element, earthing, or grounding as it's sometimes called. We've heard this term pop up. What exactly is earthing, and why is it so critical for safety?
Right. Earthing or grounding is a fundamental safety measure in electrical systems. Its main purpose is to provide a safe, low-resistance path for any fault currents, stray electricity that's not going where it should, to flow directly down into the earth harmlessly. This prevents dangerous voltages from building up on the metal casings of appliances or other conductive parts that someone might touch. There are really two key aspects to consider: the local earthing for the whole house installation, and the specific earthing of individual appliances.
Okay, let's start with the local earthing. Where is that usually done, and what does it involve? Sounds quite earthy.
It literally is. Local earthing is usually done right near where the electricity supply enters your house, often close to the kilowatt meter. It typically involves driving a long copper rod, or sometimes burying a thick copper plate deep into the ground, maybe 2 or 3 meters down. To ensure a really good low-resistance connection to the earth itself, the hole around the rod or plate is often filled with a mixture of charcoal and salt, which helps absorb and retain moisture and improves conductivity. Sometimes there's even a pipe fitted so you can pour water down occasionally to keep the area damp, especially in dry climates. The top of this earth rod or plate is then securely connected via a thick copper wire to the main earth terminal in your consumer unit or meter box.
Wow. Okay, so it's literally making a solid connection between the house wiring's earth system and the actual ground beneath our feet. What's the main safety benefit of doing all that?
The primary safety benefit of having a good local earth connection is that it provides that guaranteed low-resistance path to ground for fault currents. If there's a major fault, like a live wire shorting directly to the neutral or earth somewhere in the system, or maybe a lightning strike nearby inducing high voltages, this local earth connection allows that huge surge of current to flow safely into the earth. This helps trip the main fuse or circuit breaker quickly and prevents the entire wiring system, including the earth wires themselves, from rising to a dangerous potential. It also helps prevent overheating and potential fires caused by fault currents flowing through unintended paths.
Okay, so it's like a safety drain for large fault currents for the whole system. And then there's the earthing of individual appliances, particularly ones with metal bodies, right? How does that work?
Yes, this is the part that directly protects us from shocks from faulty appliances. For appliances that have exposed metal casings that you might touch, think kettles, toasters, washing machines, refrigerators, electric cookers, irons, there's a third wire in their power cord, the earth wire. Inside the appliance, this earth wire is securely connected directly to the metal casing or chassis.
Okay, the green and yellow wire usually connects to the metal body. And how does that protect us if something goes wrong inside?
Let's imagine the worst case. Due to vibration, damage, or component failure, the live wire inside the appliance accidentally touches the metal casing. Without earthing, that whole metal casing would instantly become live at 220 volts. If you then touched it, you'd likely get a very serious shock as the current tried to flow through you to earth. But if the appliance is properly earthed, the moment that live wire touches the earth casing, it creates a direct short circuit path from live through the casing, down the earth wire, back to the consumer unit's earth connection, and ultimately to the local earth rod. Because this path has very low resistance, a very large current immediately flows.
A huge current flows.
Exactly. And this massive current instantly blows the fuse in the appliance's plug or trips the circuit breaker, the MCB, for that circuit in the consumer unit. This disconnects the power supply to the faulty appliance extremely quickly, long before someone is likely to touch it and get hurt. The earth wire provides the escape route for the fault current that triggers the fuse or MCB.
That makes perfect sense.
Yeah.
It turns a dangerous situation into a harmless blown fuse or tripped breaker. The chapter also mentioned removing paint for the earth connection.
Yes, that's a small but important detail. If the earth wire is connected to a painted part of the metal casing, the paint can act as an insulator, preventing a good low-resistance connection. So any paint or coating should be scraped off where the earth wire terminal makes contact with the metal body to ensure it works effectively.
Good tip. Okay, so earthing is critical. Now let's look at the things we physically handle to connect to this power. Those 3-pin plugs and sockets. They seem pretty standard, but there's clearly some clever safety design built into them.
Indeed there is. The standard 3-pin plug, like the common UK type, is a great example of safety engineering. It usually has a robust casing made of a tough insulating material like ebonite or hard plastic, and inside it has the 3 metallic pins we discussed. One for earth, E, one for live L, and one for neutral N.
And I've always noticed the earth pin looks different. It's bigger, right?
You're absolutely right. The earth pin is deliberately designed to be both thicker and longer than the live and neutral pins. This is purely for safety.
Thick and longer. Why?
The extra length ensures that when you plug the appliance in, the earth connection is always made first before the live and neutral pins make contact. Conversely, when you unplug it, the live and neutral pins disconnect before the earth pin does. This provides a crucial safety window. The appliance is always earth for slightly longer than it's powered.
Ah, clever. Earth first, last out. And why is it thicker?
The thickness serves 2 purposes. Firstly, it ensures it's physically impossible to accidentally insert the earth pin into the smaller live or neutral slots in the socket. Secondly, being thicker means it has a lower resistance and can carry a larger fault current safely if needed. The pins also often have those slits or are slightly sprung.
Yeah, the split ends.
Right. That's to ensure they make a really firm, tight contact inside the socket, preventing poor connections which could cause overheating or sparking. It's all about safe, reliable connection.
So the plug itself is packed with safety features. What about the socket it plugs into?
The 3-pin wall socket is designed to match. It has 3 corresponding holes, usually with shutters behind them for added safety, especially to prevent children poking things in. Inside these holes are metallic tubes or grips that connect to the fixed wiring. The live, neutral, and earth wires coming from the consumer unit. The position of these holes is standardized. Typically, looking at the socket, the large hole at the top is for the earth pin. The hole on the bottom right is for the live pin, and the hole on the bottom left is for the neutral pin.
Right. Live, left, neutral, top earth. Got it. And just like with switches, I assume there are basic safety precautions for using plugs and sockets.
Absolutely. Number 1, again, is dry hands. Never plug in or unplug anything with wet hands. Number 2 is ensuring the plug fits snugly and securely into the socket. A loose plug can wobble, create poor contact, generate heat, and potentially lead to sparking, which is a fire hazard, and can damage both the plug and the socket. If a plug feels loose, it's best not to use it.
Good advice. The chapter also briefly mentioned 2-pin plugs, the ones without the earth pin. We see those on phone chargers, lamps sometimes. Why are they okay without an earth?
2-pin plugs are generally used only for low-power appliances that are double insulated. Double insulation means the appliance is designed with 2 layers of insulation, basic insulation on the wires, plus a supplementary insulating casing. It essentially means there are no exposed metal parts that could possibly become live, even if there's an internal fault. Because the risk of electric shock from the casing is considered negligible with double insulation, the earth connection isn't deemed necessary for safety. You'll often see a symbol on these appliances, a square within a square, indicating they are double insulated.
Ah, okay. Double insulation means no earth needed. Makes sense. Now let's talk about something that's usually hidden inside cables, but is incredibly important for getting things right. The color coding of the wires.
Yes, the insulation on the individual wires inside a multi-core cable, like the flex on an appliance or the fixed wiring in the walls, is color-coded. This is absolutely essential for ensuring correct and safe wiring. Getting live, neutral, and earth mixed up can be extremely dangerous. There have been different color codes used over the years.
Right. What was the old system and what's the current standard?
Okay, under the older convention, which you might still find in older installations, the live wire was typically covered in red insulation. The neutral wire was black, and the earth wire was green.
Red, black, green. Okay. The old way.
The new Harmonized International Convention, which should be used in all modern wiring, uses brown for the live wire,
Brown for live.
light below for the neutral wire,
Light blue for neutral.
and green and yellow stripes for the earth wire.
Green and yellow stripes for earth. Okay, brown, light blue, green, yellow now. Why the change? And why is sticking to these colors so vital?
The change was primarily for harmonization across Europe and internationally, reducing confusion and potential errors when electricians work across borders or with imported equipment. Sticking rigidly to the correct color code is vital because it's the primary way an electrician, or even someone doing DIY wiring, which should be done very carefully, identifies the function of each wire. Connecting a live wire where the neutral should be, or failing to connect the earth wire correctly, could lead to appliances not working, equipment damage, or, much worse, creating a serious risk of electric shock or fire. It's a universal language for electrical safety.
Absolutely. Getting the colors right is literally a matter of life and death sometimes. The chapter also had a brief note on high-tension wires, those really big cables you see strung between tall pylons across the countryside. Anything special about how they're made?
Yes, those high-tension cables carrying extremely high voltages over long distances have a specific construction. Instead of being one single, solid, thick copper or aluminum conductor, they are usually made up of multiple thinner wires, often aluminum strands, sometimes reinforced with steel strands in the center for strength, all twisted together.
Stranded, not solid. Why?
There are a couple of reasons. Firstly, a stranded cable is much more flexible than a solid one of the same current carrying capacity, which makes it easier to handle and string between towers. Secondly, and importantly for carrying heavy currents, the stranded construction provides a much larger total surface area compared to a solid wire with the same cross-sectional area. This larger surface area allows heat, generated by the current flow, to radiate away more efficiently into the surrounding air. This helps keep the cable cooler and reduces energy losses compared to a solid conductor carrying the same heavy current.
That's clever. More surface area helps dissipate the heat better. Okay, finally, the chapter wrapped up with some general safety precautions when using electricity in the home. It's always good to have a quick reminder of the basics, isn't it?
Indeed. It really boils down to avoiding the two main dangers, fire and electric shock. To prevent electrical fires, the most crucial thing is to ensure that all wiring, both the fixed wiring in the walls and the flexible cords on appliances, has the correct current carrying capacity or rating for the load it's expected to handle. Using wires that are too thin for the current being drawn causes them to overheat, which can melt the insulation and ignite nearby flammable materials, so never overload circuits or use extension cords inappropriately.
Right, don't overload. And what about avoiding the risk of electric shock? What are the key takeaways there?
For shock prevention, it's really a combination of all the things we've discussed. First, ensure the insulation on all wires and cables is in good condition, no cuts, cracks, or fraying. Replace damaged cords immediately. Second, as we emphasized, never touch switches, sockets, or appliances with wet hands. Keep electrical devices away from water. Third, ensure that appliances with metal casings are properly earthed via a 3-pin plug and correctly wired sockets. Fourth, make sure that every circuit and major appliance is protected by a fuse or MCB of the correct rating, and that these are always in the live wire. And finally, ensure your home has effective local earthing installed near the meter. All these layers work together as a system to minimize the risk.
Okay, that's a great summary of the safety layers. Right, let's try and bring this really illuminating deep dive to a close now. We've covered a huge amount of ground, haven't we? From how power gets generated and transmitted all the way through the wiring in our homes, the ring system, fuses, switches, earthing, right down to the design of plugs. What would you say are the absolute key takeaways for you, for our listener today?
Well, I think in summary, you should now have a much clearer picture of that whole journey, the voltage steps up and down, why high voltage transmission is so efficient, the benefits of the ring wiring system in distributing power around the home, also the critical differences between parallel and series connections and why parallel is essential for homes, the vital role of fuses and MCBs as safety cutouts, and understanding the why behind safety features like putting switches and fuses in the live wire, the purpose of the earth wire, and even the specific shape of those 3-pin plugs.
Yeah, and for me, I think the real aha moment in digging into this is really appreciating that almost every single element in your household electrical system, from those huge transformers miles away down to the slightly thicker earth pin on your plug or the color of the wires inside a cable, it's all been thought about and designed with a very specific purpose.
Yeah.
And that purpose is primarily about keeping us safe and making sure our devices work reliably and efficiently.
Exactly. It's fascinating, isn't it, how all these individual components and design choices work together as this kind of comprehensive safety net, one that we probably take for granted most of the time.
We absolutely do. So here's a final thought for you, our listener, to maybe ponder on. Next time you're walking around, try and trace the electrical path. Look from the nearest visible power line or substation, follow it towards your home, think about the meter, the consumer unit, maybe even look at the cable going into an appliance you use every day. What components that we've discussed today can you now identify along that path? And perhaps more interestingly, what new questions do you now have about this intricate, invisible, yet utterly essential journey of electricity within your own walls? Thanks for joining us on this truly electrifying deep dive.